Hello physics students. Today will be an exciting video because we are in our exciting topic of Gauss's law, and we're going to be, for the first time, using Gauss's law to determine the electric field around an object. Now remember, so far we have learned how to find electric field around point charges, protons and electrons, and then charges spread out over objects by cutting those objects into little bits that act like protons or electrons and then integrating over the object. And it was pretty difficult, pretty tedious. So today, Gauss's law will give us the electric field around spheres. So today we're going to be studying spherical symmetry, spheres that are solid, hollow, have holes in them. And then we're going to also in this unit learn cylinders that are charged up, and then also slabs like a piece of asphalt or something in a parking lot that's charged up. And we'll be finding the electric field around those various charge distributions using Gauss's law. So let's begin. Gauss's law 1, spherical symmetry. Here's our example. We have a sphere, a solid sphere of radius r with charge uniformly distributed all throughout. So like in here, if we were to, a tennis ball is hollow, but let's suppose we got a solid sphere and we could extract maybe with a needle a little piece of this sphere from the inside. It would have just as many coulombs per meter cubed as a piece on near the outside. The charge imbalance is everywhere, constant, all throughout the volume. That's what we have here. And what we're going to be doing is determining the electric field for r greater than capital R, the sphere. In other words, outside the sphere, and for r less than capital R. In other words, for inside the sphere. So we begin naturally by writing out Gauss's law. Here it is. Now notice I did a little color coordinating. This is the closed Gaussian surface which encloses the entire charge. We want to find the field out here, so our Gaussian surface has to be out there for it to get us the field in this region. But before I go on, I want to make sure you understand this very important, very beautiful idea, Gauss's law. So remember I said yes in the last video, maybe we watched it yesterday, that all of these symbols are absolutely critical, just like when you say let's eat grandma versus let's eat comma grandma, changes the meaning dramatically, tiny little comma. Same here, all these symbols are critical to say the right thing mathematically. First of all, this closed circle means the surface has to be closed off. Right now, this is not an adequate Gaussian surface because this inside is open to the outside universe. Only when you close this up and seal it off, now can you use it for Gauss's law. It has to be closed. So that's what that circle means. And then these dot products mean that the electric field, not just any electric field along the surface. If the electric field runs along the surface, this dot product will be 0 because the area vector points like this, electric field like that, 90 degrees. So there's no flux unless the electric field is pointing out of the box. Doesn't have to be perfectly out, could be just a component of it. Or into the box, then you have a negative integral here. Positive integral, negative integral when it goes in. So closed box, integrating electric field going in or out of that box is going to equal how much charge excess is in that box or shape, whatever shape it is, could be a cylinder, could be a sphere, over this constant epsilon 0. Those are the ideas of Gauss's law. You need to know all those symbols and the meanings behind them. So we proceed. Now, you do need to know a little bit of the distributed charge unit, because what we have to first reason, we have to decide what the shape of our Gaussian surface will be. We know that because this is a sphere, we need a sphere. Otherwise, Gauss's law will be true if we put a rectangular box around this sphere, but it will not be useful. It will not give us the answer that we're looking for, because in order for this to give an answer, we need this integral to become easy and trivial. And I know from my distributed charge unit, if I have a piece of charge here producing an electric field like this at the surface, symmetrically on the other side, there'll be another piece of charge producing an electric field like that, caused by that little bit of positive. So the symmetry means that the electric field, no matter where you are on the sphere, will point directly out, like this. And furthermore, because of the symmetry, all these electric field arrows will be the same length, even though I'm probably not drawing them the same length, I'm trying to. So they're perpendicular, same length. What that means is because these are all perpendicular and constant over the integral, first of all, the dot product goes away because we have E dA cos of 0 degrees, which is just E dA times 1. So the vector signs disappear, and you could take the electric field out of the integral because it's a constant because of the way I drew my Gaussian surface. So now that it's out, all I'm integrating dA is dA. And just like when I integrate dx, I get x. When I integrate dA, I get area. Area of what? My Gaussian surface, which is a sphere. What's the area of a sphere, or the surface area? This is something you have to remember, 4 pi r squared. Don't worry, we're going to be using it a zillion times by the time the test comes around. This will be like you could recite the surface area of a sphere in your sleep. So E times area, 4 pi r squared. Now what's the charge enclosed in our Gaussian sphere? Well, all the charge inside of our sphere, our charged sphere. It's Q is all inside our sphere, so we could just put capital Q. So solving for E, we just move the 4 pi r squared to the other side, and we get this. I always write the constants in epsilon 0 in the front. It's not necessary. But the reason why is because this is the Coulomb's constant K, and it helps us with the unit analysis. So remember I said you could compare the electric field formulas to Coulomb's, the electric field formula we learned in point charges, KQ coulombs over r squared meters squared. And basically you see that we have KQ over r squared. So we didn't even technically need Gauss's law for this, but because the electric field outside this sphere, even though it's not a point charge, the electric field is the same as if all the charge were at a point at the center of the sphere. Kind of interesting. So that's the electric field outside the sphere. Now, before I move on to the next example, I just want to point out that this step is not necessary. When you're solving this, you could do it with 3 lines. Remember, I kind of promised you that in distributed charge. 3 lines, I said, and you get the answer. So this is just for me to show you the thoughts of where this stuff comes from, so it's maybe hopefully helping you understand what all these symbols mean. All right, so I haven't paused yet, so let me pause and give you a chance to jot this down if you need time to catch up. Okay, well, we have to go on to part B, and by the way, there's an example 2 coming too, so that's coming up. So part B, well, what about inside the sphere? Okay, now KQ over r squared will not work. Okay, so here comes the magic of Gauss's law. Okay, without it, this would be a terribly difficult problem, but here's the solution. So what does it mean? Well, maybe I'll explain it so that in case I don't want to stop and copy, then you might make a mistake. So we apply Gauss's law. How do we first draw the Gaussian surface? We got a sphere, so we better not draw a coffee can cylinder or box. We better draw a sphere. So the Gaussian surface, once again, matches the symmetry of how the charge is distributed. Okay? So later we'll be studying cylinders, then this Gaussian surface will be cylinder, okay? But here we got a sphere, but we want the electric field inside, not outside. So we don't draw a Gaussian surface outside, we draw inside, a smaller sphere within a sphere. So this is only in our imagination. We're imagining that we could, like with some kind of laser, cut out a little portion of that sphere on the inside. Okay, so there it is. We're applying Gauss's law to, now notice I'm using a different color than over here because it's a different surface, so I like to be nice and organized. I write out Gauss's law always, okay? The left side for spherical symmetry will always be the integral E times 4 pi r squared. So see, technically you're integrating, but that's as complicated as the integration gets with this, with today. So, but the challenge will be to figure out how much of the charge is inside our Gaussian surface. Because not all of it is, right? Some of it is outside over here. So what we have to do is first use the concept of charge density that we learned in the last video or earlier video on distributed charge. Charge density, you could spread charge over a line that's lambda coulombs per meter. You could spread it out over a surface like this, and then we'd use sigma, and that'd be coulombs per meter squared. Or you could spread it into 3 dimensions, and then you use the symbol Greek letter rho, and it's coulombs per meter cubed. So this is the coulombs per meter cubed, the density of the charge in our sphere, times the meter cubed, or in other words, the volume inside here. So we'll have coulombs per meter cubed times meter cubed will be the coulombs inside of our Gaussian surface. So next we need to figure out what this rho is right here. And to figure out the charge density, you just do total charge over total volume. One other formula you have to remember today, the formula of the volume of a sphere, the volume, not the surface area, the volume is 4/3 pi r cubed. And with the radius for the whole sphere being capital R, we do this right here. So this is total charge, total volume. Then we multiply by the meters cubed of what's inside there, 4/3 pi little r cubed, which little r is the radius of our Gaussian surface. And this will basically give you some amount of coulombs less than Q, maybe like half of it or a third, depending on these ratios. But not important. Now what we do is we just solve for E. Notice the 4/3 cancel, the pi on this side cancels. We divide both sides by 4 pi r squared, and it leaves us with this. So now this is more complicated than this formula. So I really recommend a unit check here. Remember, we need always the units of K, Q over R squared. That's what we need from our formula. So we've got our units of K here. Even if the 4 and the pi weren't there, we've got the 1 over epsilon 0. So that satisfies the units of Coulomb's constant. Then we've got coulombs up here and a meter. Then down here, we've got meters cubed. And so you could see that this basically becomes meters squared, and we have the right units. And it looks like our formula is of the right form. Again, if I lost this somewhere along the way, the little r, then I would be like, oh, wait a minute, I got meters cubed and bottom, something's wrong. I go back and look for a mistake. So that's the value of that. Last thing before we move on to example 2, we got 2 formulas, and very often a popular thing in Gauss's law is to graph the electric field for all the radii, basically these functions. So let me just make a little room, and I don't think I've paused yet, so let me pause, give you a chance to jot that down. Okay, let's now sketch the graph. So we got electric field versus radius. The key point is right here, the radius of the sphere. That's where we go from one formula inside the sphere to the other formula outside the sphere. And so the formula for inside the sphere for r less than capital R is a linear graph. This is r to the 1 power. So all the other constants just change the slope, but the graph is linear and rises to, oh, you know what? And I recommend this. See how it has a little wave to it? I go like this, proportional to r, because when you're sketching these, hey, who's perfect at drawing a straight line? Well, look, obviously, I can't put my hand up for that one. So you want to make sure you don't lose points just because maybe someone looking at it grading says, oh, they think it's a curve, -1 or whatever, because you didn't know it's linear. So proportional to r. I don't know if that looks clear enough, but proportional to r. And then after that, out here, it's a 1 over r squared. So at twice the radius, we'll have a quarter of the electric field, and it'll be this kind of descending curve. Oh, electric field. The other thing that's popular is, or sometimes required, is to put the value of what the electric field is at the transition point where we go from inside the sphere to the outside. In other words, at the surface of the sphere, we could put capital R into this formula or that one, we get the same answer. It's easier to put it over here. And maybe just for, yeah, I'll do this. Q over 4 pi epsilon 0 r squared. And see, here I wrote it all. I didn't separate out the 1 over 4 pi epsilon 0. Perfectly fine if you combine all into one formula. So there's a graph of the electric field as a function of radius. Oh, and also I would put proportional to 1 over r squared also to indicate that I understand. Sometimes you might draw it quick and it looks like a straight line. But we put that, now everyone knows you know it's a curve that goes down like that. All right, let me pause, give you a chance to jot the graph down. All right, example 2. Let's move on. All right. Let me see. Oops. Uh-oh, a little scrunched up. All right, well. So here's the shape that we're dealing with. We're dealing with a sphere, first of all. And I didn't write it out, but you know, either the test or textbook would give you a diagram, or write it out in with better words than what I did. And then, so then this is now capital 2R. And then there's a hole that's half the radius, so 1R. And that's R, the hole. So the charge is spread through that volume. Empty cavity in the middle. So we want to find the electric field in the cavity, within the charge that's uniformly distributed within this area, and then outside. So let us begin. For part A, once again I've got a sphere. I need to draw a Gaussian sphere. And it needs to be, if I want the electric field in here, it's got to be inside there. So let me just draw a small sphere like this. Okay, so I'm applying Gauss's law to that sphere. Once again, we need all these important things, the vectors, the dot product, the circle, Q enclosed over epsilon 0. Now, if you look, there's no charge in our Gaussian surface. So 0 over epsilon 0, 0 over anything is 0. So basically then, we have E times 4 pi r squared equals 0, divide by 4 pi r squared, and we can just write E equals 0. So that's all the work you need to show in something like that where the electric field is 0. You don't have to go through more detail than that. Write out Gauss's law, set equal to 0, and then write E equals 0. Done, okay? No electric field. Even though it's surrounded all by charge, Gauss's law is telling us there's no electric field inside the hole. Interesting. Part B is a little bit tricky. All right, so I don't remember, did I pause? If not, then here's a chance to jot that down. Okay, so maybe I'll make a little bit more room because, like I said, this one's the trickiest one we've done yet today. Okay, so next we want to draw a Gaussian sphere. We want the electric field in here. We've got to draw a sphere that goes through this region. So what we'll do is just go like this. Okay, there it is. And I apply, oops, B. Let's apply Gauss's law to that. I'm starting it to the left to make sure I have lots of room here. E dA for that surface, right? That'll equal Q enclosed over epsilon 0. Okay? So, the left side, once again, we could just write E times 4 pi r squared. That's what the integral becomes. E times area of our Gaussian sphere. All right, now, what we're going to do to figure out the charge in here is use rho times volume again. Okay, so that's rho v over epsilon 0. You know what? This might have even been too high. I'm going to wait to write this after I draw. Okay, so this whole big fraction here. Okay, so the rho. What I need to do is figure out the total charge over the total volume of only where the charge is. So before I did Q over 4/3 pi r cubed, but the r is now 2r. So I go something like this. Now, if I stop there, be a bit of a problem. I would be basically saying that the charge extends all the way to the center. And it doesn't. There's no charge in the hole over here. So I have to subtract off the hole for the volume of just where the charge is. So it's the total volume minus the hole, which is just 1r cubed. So there's the charge density. Okay. Now that's the coulombs per meter cubed of the concentration. What I need to do is take that coulomb per meter cubed and multiply by meters cubed to get the coulombs inside. Now, what's the, let's see how this color shows up. Oh, that's a nice one. What's the volume I multiply? The volume where the charge is inside of our Gaussian surface. Basically, that volume. Okay? So, what's that volume? All right, well, it's going to be similar to this. We can say it's the total volume of our Gaussian surface, or our Gaussian sphere, oops, a little bit bigger. Okay, so 4/3 pi little r cubed. Let me just make sure that pink shows up. Yes, okay, good. So that just determined the volume of this entire sphere. But the charge doesn't go throughout this whole area because there's a hole where there's no charge. So I need to subtract off that hole to just get the volume of where the charge actually is. So 4/3 pi r cubed is right there, the volume. Now I subtract off 4/3 pi r cubed of the hole, which is radius capital R. Q enclosed over epsilon 0 equals E times area. So, pretty tricky, right? But you'll master it, I'm sure. Now what we just have to do is do some algebra. Notice the 4/3 pi's are common here and here, and here and here, so they could basically be crossed off. And what I have is 2r cubed. So I have 2r times 2r times 2r. 2r, 4r squared, 8r cubed. Okay? So I got 8r cubed here minus 1r cubed, which is 7r cubed. Okay, so moving on here, q over 7r cubed times r cubed minus r cubed, all over epsilon 0 equals that. Now I divide by 4 pi r squared, and I'll get the final formula here. So the 4 pi epsilon 0 and the 7 give me 1 over 28 pi epsilon 0. Then what I have is the r squared. Let's see, how do I want to write this? Yeah, what I could do is then say I've got q times the r squared, and this r cubed just become r, minus the r cubed over r squared. So there's the formula for the electric field. You know what? Maybe it would look better if I put that level with the parentheses. Or I could put the q on top there. Again, any format that's compatible. Before we move on to the last part C, what I want to do is just do a unit check. Look how complicated that formula is. Did we make a mistake? Let's do our first check. So we need the constants of K coulombs per meter squared for electric field. 1 over epsilon 0, forget about the cons. 1 over epsilon 0 is like units of K, good. Then we've got a coulombs. Then we're multiplying, oops, see, I caught the mistake, good. What I'd be multiplying by is some number of meters. And what now I see is, oh, I made a mistake. What happened to the r cubed? I forgot it, see? And I didn't do that on purpose, by the way. That was a real mistake. It may look like I staged that, but I didn't. So we got q over r cubed. Okay, so there's my coulombs. Then all in the parentheses here, I got meters minus some other number of meters. So this is all just meters. And then down here, I got my meters cubed. So we see the unit check works out. Okay? So there's the formula for the electric field. Last one. This one's going to be nice and easy. The electric field outside here. So I need another Gaussian surface. I haven't used green yet, so sphere, I got to draw a Gaussian sphere. This time I want the electric field out here, so I'm going to draw a sphere out here. And let me pause first. I'm going to do some erasing, but let you get a chance to jot that down. Okay, so here's my Gaussian sphere. I'm going to apply Gauss's law to find the electric field out there. So, again, you've always got to start by writing out Gauss's law in its full glory, right? All the parts that are included. The dot product, the vector signs, the circle. There we are, okay? The left side, E times 4 pi r squared. And then if you look, the Q enclosed, nice and easy. Just capital Q. It encloses all the charge of our sphere. So now I'll erase, make some room. And I have E times 4 pi r squared. Q over r, epsilon 0. Divide by this, and I get my final answer of just the point charge formula. Don't even need to do a unit check on this one because it is the formula of a point charge. Again, it's the same as if you took all that charge and concentrated in the middle. So let me pause and let you, oops, I forgot to label part C. Okay, pause to give you a chance to jot that last part down. One final thing, you might guess, graph. Okay, so we got to create a graph of these three functions in the three regions. So I guess I could make space over here because I'm done with the derivation, but I'll leave the formulas. Okay, so my axes. Now there are two important. There's 0 radius, there's capital R, and then there's a transition at 2R. And then from there, kind of just goes on. So those are the key points. So we saw for inside the hole, remember this was easy to forget, but it's a sphere with a hole in the middle. So inside that hole, there's no electric field. So maybe it'll show up better if I do a different color here. There's the E equals 0 inside the hole. Then it increases by this function between R and 2R. How do you graph that? It turns out that on the AP, when they have an answer key, they often say, for some reasonable curve. Okay, so make a reasonable curve of that. And your choices are, it's going to obviously start from 0 and rise up. And so is it this or is it that? Well, I think if you drew either one, you would get credit. It's a reasonable curve. But it turns out that it's this one. How can you figure that out? I always tell students, if you want to, only if you have time. If you don't, just quickly do it and go on to the next question because you're short on time. If you have time on an AP test, forget about all the constants like this, all these, and just take out the R variables. We got R over here minus something R to the minus 2. So that's the essence of the R dependence. How do you tell if a function is concave up or concave down? You take the derivative twice. If your answer is negative, concave down. If it's positive, concave up. So let's take the derivative once. This is 1 minus negative 2 R to the negative 3 power. Okay? So then we take the derivative again, and this is now positive, and we get 0 times positive 2 times negative 3 times R to the minus 4th power. Oh, I actually was wrong. We get negative 6R to the negative 4th is the dependence of the second derivative. Concave down. Okay. And I promise, that was not done on purpose either. Okay. Concave down. Okay. And then this is just a 1 over R squared. You know that. We've dealt with that before. So this will be down like this. And here we could definitely label this proportional to 1 over R squared. And the last thing, the transition value. The easiest thing to do would be plug in capital 2R into here, giving us 4R squared. And then combining with the 4 gives us 16 pi epsilon 0 Q over R squared. And again, here I just combined it all into one fraction. So there's the electric field as a function of radius. All right? So there it was. Exciting day. I found it exciting. I hope you found it exciting, or at least somewhat interesting. I'd settle for that. But fascinating, Gauss's law. We can find the electric field much easier than if we had to do the KQ over R squared integrated approach. So what we do is for a sphere, we draw a Gaussian sphere either outside or inside this larger sphere. And then we do Q enclosed over epsilon 0. And the Q enclosed can be sometimes the tricky part. Total charge over total volume times the volume, giving us altogether coulombs inside our Gaussian sphere. And then the left side, E times 4 pi R squared, all the time with spheres. Okay? So I'll see you in the next physics video where we'll be doing spheres, but conducting spheres, metals. and in the next video. I'll see you then.